So it is my great pleasure to introduce Geoff Orth from Medtronic.
I have worked at Medtronic now for 12 years in a variety of roles, in either doing the technology myself and putting my hands on things or managing other people in that process. So I tried to put together some slides that would allow us to look through my career, and I definitely want to leave some time at the end for questions here. So I'm gonna go ahead and keep moving. So this is my story. I mean, I used to be your age. I remember high school. I remember middle school, but this is what I look like before that. Those are tough skin jeans that they used to sell at Sears. This was my grandfather out in Illinois. My grandfather was an inventor. And I didn't spend a whole lot of time with him, but the time I did, I loved working in the shop and working with my hands. You know, this is me, probably 13 or 14, working in the shop at my parents' place. You know, fast forward to me with my two girls, again, you know, getting our hands on things and working on things together. You know, why do I bring this up is that we've all got a story and it all starts somewhere. I want to tell you a little bit about my story, but I also want you to think about your story. And part of that is figuring out where you want to go and what the next chapter is. You know, one of the things that I, you know, encourage people that I mentor and encourage my family and people that I meet, or when I go to high school events, is, you know, what's your work and what's your passion? And I guess I would really encourage you all to think about what your passion is. I've always loved mechanical things. I've always loved taking things apart and putting them back together. I've always had an intense curiosity for how things worked. So, you know, even to this day, you know, I love changing the oil in the car. Every time we get a new car, it's like it's a challenge. It's like, hey, you know, can I make this work? But being able to, you know, go from the things that, you know, are a bit more, you know, typical, changing the oil in your car, to working on devices for humans and heart valves. And this is a, you know, a setup here. This is a you know, a silicone molded version of the heart that we use to test things. I mean, if I screw up an oil change, I mean, you know, it could cost me some money. You know, got to call AAA. If you have some difficulties with the patient's heart, it's kind of a little bit of a higher bar. But they all are very related. And, you know, I think after having a 30-year career, I think I've done a reasonable job of aligning my passion and my work. You know, solving complex problems, and maybe, you know, we can kind of go back to the oil change analogy, right? Oil change, pretty straightforward, but, you know, hot things, you can cause yourself some trouble. To the human, I mean, there's a lot more going on there, and some of this requires, you know, hands-on building things, but a lot of it requires, can you understand the problem? Can you understand the heartbeat? You know, can you understand what's going wrong? Because as opposed to building something with wood or metal, dealing with a patient, I mean, there's just a lot other different ways that you have to think about the problem. So one of the things that I really enjoy doing is solving complex problems. So again, on the left here, this is a machine shop at Medtronic, and this is actually a training in one of our cath labs in Minneapolis. So working in medical devices, you know, one of the things is, you know, can you make life a little bit better for others? Can you leave things a little bit better than you found it? You know, I think we're in a world that you can see a lot of people are out for making themselves better. And, you know, I didn't really necessarily talk about, well, I picked engineering, you know, because it, you know, gave me a certain lifestyle. You know, one of the things I love about working for medical devices is you get to change people's lives. And I get to see it in the patients. But this is my dad and my mom. They're both in their 80s. But a year ago, my dad got a new aortic valve, an engineered aortic valve, very similar to the stuff I work on. But, if I roll it back to my, 15-year-old self, I never thought that the work that I would do would not only change people's lives, but would be able to change my family's lives. Maybe a bit of a rough transition here, but this is talking about curiosity and failures. In my job and when mentoring people, it's one of the questions I always ask is aren't you a little bit curious about how this works? I think I probably have an extreme case of curiosity because I'm kind of curious what makes it work, but very often I learn a lot more by what makes it not work than what makes it work. Because a lot of times if you do something that works, you're just lucky. But when something doesn't work or goes wrong, you learn a lot. Here's my favorite one with the mousetrap, right? It's like sometimes you have these problems that keep showing up, and you got to solve them, and they kick your butt, and you're kind of dazed, and you sit down and you got to try it again. It's like, okay, well, at least next time I'm going to wear a helmet, and see if this comes out a little bit better. And then there's judgment. Sometimes you do something and it was just plain stupid, right? Here's the oven in our house is brand new, and I was doing some car work and I needed to cure the paint on an exhaust system. So my wife walks in and she looks in a brand new oven, and there is me with smoke coming out of the oven with me curing the paint. Probably something I'm not going to do again. But again, I learned a lot for that. I mean, nobody died and we didn't burn the house down, but probably could make better decisions. This was probably the highlight of my life in medical devices. This is a patient. His name is Andrew here, and so this would have been 2 years ago. He was implanted with a product that I worked on. I don't know if you can barely see it. The physician's holding it in his hands here, but this is Harmony, and we're going to talk a little bit about this device. But this is a new valve for his heart. But he is a 21-year-old heavy equipment mechanic out in Fresno. And he couldn't get to work. He was short of breath. Things were not going well for him. He got to Harmony. He comes back a year later. He's smiling. He's excited. He's getting married. This is his fiance that's next to him. Again, a life-changing event. The bit of irony on this is he was one of 20 valves we put in, but they were difficult to put in. So we went back to the design and changed the design. So at some level, again, depending on the lens you're looking at it, if you're looking at it this way, it's like, Geoff, man, you could have made that valve better. You could have made it easier to go in. And it's like, yeah, I could have, but we would have been a year or a year and a half later. But from Andrew's view, he's like, dude, thanks for doing that. Thanks for pushing to get it here because my life is forever changed because of that valve. So again, careful with your failures. Always be curious. Don't beat yourself up. My favorite thing to teach people is, well, it was just a bad idea on the way to a good one. So I'm going to transition here a little bit to just talk about kind of what my day looks like and what are the things that I work on. My day, even before COVID, looks exactly like what we're doing here, except you appear to all be a lot more polite than the people I usually deal with. And I mean that in a funny way. I mean, I am on the video. We have team members in Ireland. We have team members in Mexico. We have team members on the East Coast. And we all talk about complex problems and how to solve them. So I'm going to just kind of focus in. We're going to talk about heart disease, but we're going to talk about it from the perspective of heart valves. I spend a lot of time in this area here, so I may go flying through something and write your question down, and let's talk about it and straighten it out at the end here. So valves, your heart, I'll give you the answer here. Your heart has 4 valves in it. But what does a valve do? A valve, you know, turns on and turns off, right? You know, you have a valve on a, you know, this is a water bottle. You have a light switch. Well, you know, a light switch is not, maybe you don't consider a light switch a valve, but what does it do? It lets the electricity in, shuts the electricity off. Let's just call it a valve. So this is your heart, and let me, I'm just going to change my pointer. Here we go. It's kind of small. All right, can you see my pointer a little bit here? Milo, is that okay, or should I do something different here? Let me try this. There we go. There's laser pointer. I like that one better. So here's your heart, right? So if you take your hand, right, make a fist with your hand, right, and kind of like maybe doing a defiant Pledge of Allegiance here, right? This is your heart, and this is where your heart sits. So how you're looking at this, though, right? You're looking at me, right? So if this was your heart, it would be like that. So it's my butt. This is your heart, and this is how it sits in your chest. It's a little bit tilted down into the right. If you know you get here, right? This is how the blood flows out of your heart. So it comes out of the aorta and flows over this way. It comes back from your body, comes in this valve, comes out of this valve, and goes into your lungs, and it goes into your lungs on this side, right? And then it comes back out of the lungs, and then we repeat the whole thing again as we come through there. And I know that it's like, wow, that went by really fast. Let me erase that. But it's important to understand that these, at some level, are a super complex problem that only doctors can deal with. But on the other end, they're just a valve, right? I mean, they just turn something on and turn something off. And these are problems that we can all solve together. You know, one of the interesting things about these valves, and you can see it a little bit better in this picture here, is these valves have leaflets. So here is your pulmonary valve, and I'm just going to outline this leaflet right here. Outline this leaflet right here. Whoa, getting a little crazy. And outline this leaflet right here. Actually, this is your aortic valve. But you know that's a 3-leaflet valve. This is your pulmonary valve. It's got 3 leaflets. You know, this is your mitral valve over here, and it's got 2 leaflets right here. And then this is your tricuspid valve, and it's got 1 tricuspid, right? 1, 2, 3 leaflets in it. And this is, again, if you cut me off right here, I should probably say this. If you like cut me in half and then you looked down my neck, that is what your heart looks like. Doing that. So I'm going to keep moving here. And we'll pop the next slide. So I think this is nearly one of the coolest slides that I've ever seen. And this talks about your heart, electrical, mechanical, and chemical. And I don't know how well this is playing for you here, but right, you see the valve. There's a valve here, tricuspid valve with the blood coming in, goes through the pulmonary valve. This little T, right, you'd have a lung right here, and you'd have another lung right here, right? It comes back out of your lungs into the left atrium and then into the left ventricle, and then it goes out through your aortic valve. So, right, valves and pumping. Well, there's also these electrical signals that are driving these pumps and telling these, you know, when the ventricle needs to contract, when it, you know, needs to open and shut. So there's an electrical side of this. And then the other thing is there's a chemical side of this. if you have too much water, if you have too much salt, if you have a chemical imbalance, it can affect, right? Anybody ever seen heat stroke, right? You just kind of like fall over, you can't do anything. Well, you don't have enough water and your temperature and your chemistry are wrong, so you stop functioning. There's a version of this that affects the heart. It's called heart failure. Now, heart failure can be your valves aren't working. Heart failure can be you've got electricity issues, but heart failure could also be your chemistry is wrong. But the really cool thing, I mean, if you feel your heartbeat, I mean, all of us are doing this right now. I mean, if I look at my watch, I'm currently about 65 beats per minute. But everyone is doing this right now. Your heart, everybody's got these electrical signals. Your valves are you know, opening and closing in cadence. It's moving blood through your body, and everybody does this. It's great to be involved in this amazing complex system. So I'm going to go ahead and see if I can get these to play. There we go. So these are actual pictures of an aortic valve, and I'm not sure how well they're playing, but rather than blood, we've got saline in here, and you can see how thin these leaflets are, and this is right. This is how your heart has grown, and this is what makes them work. And you can see the 3 leaflets opening and closing. I had no idea that a valve you could see through could last your lifetime. I mean, when I saw this, this just absolutely blew me away. How you get this picture, right? This was done as a setup. This is somebody's heart that was no longer needed. And we set this up in a laboratory and filled it with saline and had it pump. So one of the diseases, and I bring this up because the patients that I work with are really your age. That, you know, on the left here, we've got a normal heart, and then on the right, we've got a diseased heart, and this is tetralogy of Fallot. And there's some differences here, but tetralogy, tetra, right, 4 things. And the 4 things are narrowing of the pulmonary valve, right, so the baby is born blue, thickening of the right ventricle, the heart's not pumping the right way, and then there's a hole between your left and right ventricle, and then the aorta is down, is in the middle of the heart. And again, so tetra, 4, and Fallot, some dude named Fallot, Dr. Fallot, right, 1850. Did all this without CTs and ultrasounds, you know, did this research. But this is one of the things that happens. It's called a congenital heart defect. So not going to get into this, but again, you're looking at this. This would be your left lung. This would be your right lung, right? Here's your heart. So this patch would be, you know, on the back of your hand, and this is one of the things, one of the surgeries they do. This is another, it's called a conduit repair. But these typically are done when, you know, this surgery is done before you're 2 years of age. This surgery is typically done before you're 12 years of age. 1 in 100 births. So I don't know how many people are at your school, but it is very common to run into somebody with a congenital heart defect. It's very common in what's going on. Let's see what else we've got here. You know, how you fix a valve. You know, we talked about heat stroke and lifestyle. I mean, healthy diet, you know, being a person that exercises and watches what you eat, you know, failing that, you know, medications, low blood pressure. When you start having structural issues with your heart, when you start having bumps and restrictions and calcification, that stuff is not reversible without an intervention. You can go in with a balloon and you can kind of balloon things open and try to restore the flow. You know, ultimately you end up with replacing the valve either by surgery or by what we do, which is a transcatheter valve. And I've got a video that I'll run of the transcatheter valve, but I showed you a picture of sorry, I just need to change my pointer back to turn my, I showed you a picture of the valve like it was you were born with, but this is a picture of the valve that Medtronic makes. And this is a high-speed photo of the valve. You can see a metal frame around here. And this is what, you know, technology and a huge group of people working together can put together to make that happen.
Students could take a look at the worksheet in the chat and let us know if you have any questions about that. And please put any other questions in the chat. And I just wondered, why did you choose engineering and when?
So I chose engineering at the end of high school, and I chose mechanical engineering really because, you know, at the time it was something that fit with my curiosity of how things went together, and I figured it could be something that I could build on. And I really didn't know where I was going to go with it, Milo. And again, you know, with school, I mean, you choose something, and there were aspects of the curriculum that were very difficult, and there were times that I felt like quitting. You know, getting through the math sucked at times. But again, I think that these are the things you do in life that have turned out well. So it was a bit of a guess, truthfully. But you know, if you kind of look at the story, my story, it kind of ended up in a good spot.
Stefan asks, is there a chance that the body will not accept the mechanical device or any of the added mechanisms in the heart?
You know, absolutely. It is not quite the same as a transplant, right? You hear somebody, well, you know, they got a kidney transplant and, you know, your body's rejecting it. So it's not at that level that we have to put down, you know, anti-rejection or rejection drugs. Typically, the valve and the leaflets are what we say are inert, which means they're not living. You know, the tissue is fixed, right? It's basically turned into as close to a polymer as tissue can be. But, you know, rejection, you could get the biggest type of rejection you see is an inflammatory response, right? Where the body goes, hey, I've got an injury here and I need to do something about it. And it starts, you know, sending T cells and they get over there and they start getting angry, and you could end up with an infection and making the valve not work. That is not what typically happens. These are typically, you know, they go in, they last for 10 years-ish, something like that. But, you know, there's always a possibility that something doesn't go as planned.
Here's a question from Carrie. I heard of a proposed idea for a sort of sleeve that fits over the heart, keeping it beating similar to a pacemaker. Have you heard of this idea? And what do you know about the mechanics of how it would work?
Yeah, that's a good question. So I don't know if I'm familiar with the sleeve, but it's kind of like, I mean, it's a little like CPR, right? When somebody loses, you know, stops their heart, you can compress it from the outside. So, you know, if the sleeve compress the heart or, you know, compress it in rhythm, absolutely, absolutely that could work. And, you know, I think it's a good comment to make because they're, you know, in complex designs, there are always trade-offs. Well, what do you mean, Geoff? Well, let's say we go in and we replace your aortic valve. Well, let's say we press on one of the electrical centers in your heart and now you have abnormal beating or you have an arrhythmia. And then we have to put a pacemaker in to regulate that electrical control. So there are patients that, you know, pacemakers may not work or valves may not work in something like a, you know, a compressive sleeve, you know, may solve some problems for some people. And we would call that an unmet patient need, right? There's patients out there that need something that we just don't have a solution for. But I could see that working. got a few technology things we got to figure out, but we can do it.
Here's a question from Aaliyah. What type of metal is used in the devices, and how do you test the devices to see if the heart takes to it?
Yeah, so good questions. Good questions there. The metal is nickel titanium, and maybe you can guess from the name that it is mainly nickel and titanium. One of the advantages of, and one of the things we look for materials that go in the body is that they don't rust and don't corrode. So titanium has a feature that it puts a electrical shield over itself. It's called a passive layer that keeps the body's chemistry from attacking it. Nickel titanium has a few other interesting things it does. It is probably more, it is more break resistant, has more resistance to the heart's beating than a standard steel does. You ask, how do we test it to see if the heart will take it? So really there's three very broad levels of testing. And maybe I'll cheat and I'll put a fourth one in. So the one that I would encourage you to do is making math models and using a computer to analyze stresses and strains and corrosion and expected behavior. Because I think very often you can learn a lot from modeling. The second one is benchtop testing, which is, right, you put it on the bench and you bend it back and forth and you count how many times before it breaks, you know, or you pull it and see what force it breaks on. The next one is, and again, you got to be very careful and you do this and you have to be very respectful, but you know, before we use this in a human being, we typically look for an animal model. You know, a lot of times we will use pigs or sheep, and we will test these devices, you know, literally in place you know, in the heart of one of these animals and ensure that it works. So once we've kind of cleared these first three barriers, the fourth area we tested is in patients. So like that patient, Andrew, I mean, the device wasn't commercially available. He signed up for a medical device trial, and we put it in him, fully expecting it to work, and it did.
Okay, we have a question from, what makes the mechanical valves open and close?
Yeah, so that is a good question. They are only with flow. So when the heart pumps and the fluid pressurizes in the ventricle, those leaflets open up under that pressure because there's high pressure on the lower side here, and the blood has moved on top of that, so there's low pressure. So things will go from high pressure to low pressure, and they pop open. And when the heart has stopped and the ventricle is completely contracted, it'll start to open, which will create a low pressure on this side, lower than the pressure above it, and the valve will come and it will close. So the valves don't have any like strength or muscles. It is strictly following the flow of the pump. So when the flow goes out, it opens. When the flow comes back, it closes, and it has to do with the differential pressure. Same reason an airplane flies, right? Gets up to speed on the runway. The pressure on the bottom of the wings is more than the pressure on the top, and the wings lift. Maybe not the best analogy, but I hope I answered the question.
Mm-hmm. Carrie asks, if a patient is diagnosed at birth with a heart defect that isn't immediately life-threatening, would it be better to have surgery right away to prevent problems when they're older, or to wait until they're older?
Yeah. So the question that you have to answer is, will it have developmental effects, right? Like, will you not be able to run and play with your friends, or will you be underweight or not develop muscles? Because you are absolutely right. If you can get by until you get older, that would be much better than you know, some type of invasive surgery. one of the things with putting valves in on catheters rather than cutting people open is that it allows us to intervene earlier, right? You know, one of the examples is people are born, you know, you ever heard somebody says, well, they got a hole in their heart, right? They've got a PFO or a patent foramen ovale or an, you know, an ASD, an atrial septal defect. And now rather than surgery, they put this, even with this tiny little baby right at the bedside, they guide a tiny little catheter up and pop a little plug in there. And it solves the problem, and the baby oxygenates better. And you know, there is kind of the good side of it, right? Most of these patients, if they can oxygenate blood, these babies, you will push the surgery off at least until they're 2 years old. If they're born and they're blue and they can't breathe, they go right to surgery.
How much do you have to customize the valve for each patient?
We don't. Harmony makes 2 valve sizes and 1 delivery catheter. Now, you know, that said, you know, we went out and measured probably 1,000 patients. And part of the complex problem we're solving is, you know, how big, how long does this device need to be? How big does the valve need to be? So there's this, you know, don't hold me to this, but there's roughly about 30% of the patients that we don't have valves that fit. So we've got doctors, you know, calling me up, hey, Geoff, you know, need a bigger valve, need a shorter valve, you know, need a different delivery system. You know, can we make some more of these? So we had to make some tough decisions. So there's patients that either will go to surgery or back to Carrie's idea, right? I mean, there's going to be somebody that's going to come in and go, well, Harmony doesn't fit, but boy, do I got an idea for you. I got this sleeve that goes around the heart, right? So there's room for multiple technologies here.
Mm-hmm. Is there any way the device can fail while in the heart? Would you have to replace it? Would this make the procedure more difficult?
Yeah. So absolutely the device can fail. Usually what happens is, I mentioned, so these leaflets that are put in are cut out of porcine pericardial sac, right? So cardium is heart, right? So pericardial, peri, outside of the heart, there's a sac that goes around your heart that kind of allows it to do its thing without sticking to your lungs and your spine and everything, right? So when they slaughter pigs to make bacon or whatever they make out of pigs, Medtronic takes these sacs and we cut them out and treat them. So these sacs go in as these leaflets, and they're completely dead tissue, but what happens is you get some collagen that grows into that surface. And that collagen actually helps. You know, you've probably heard it, you know, with face makeup and things like that, they use collagen. This collagen helps them be more elastic and last longer. Well, you know, too much of a good thing. At some point, that collagen will build up to a point where the valve will stop working. Now, what do? Well, the good news is you've got a hole, and you can go in there and place another transcatheter valve just inside that valve. And it's got a really creative name. It's called valve in valve. So the good news is that once you have this structure in there with the valve, if the valve stops working, just go in with another valve, open it up on the inside, and, you know, you will typically get, you know, another 10-ish years, right? And the technology improves. So hopefully, you know, Andrew, the patient that got a valve 2 years ago, let's say his valve stops working at 8 years. So 6 years from now, he gets another valve. Well, maybe this valve goes 14 years, right? So now he's 6 plus, he's another, so he's 41 years old. Well, maybe the next valve he gets lasts 20 years, right? I mean, at some point, you're going to have a lot of valves in that guy, but that's the idea.
Can you explain exactly what a catheter is and where it gets inserted?
Sure thing. So a catheter in the most simple sense is just a piece of tubing, right? And, you know, they talk about it like if you have surgery and they have to cut a hole in you and it's infected, they put a drain in you, which is a drain catheter to drain any, you know, bad fluids out of you. They put a feeding tube. A feeding tube is a catheter, right? It goes down your throat. They use it to do that. So all a catheter is a long tube that does something. If you're a space fan, think of a catheter as a rocket, right? A rocket just delivers its payload and then gets out of there. Nobody, nothing fancy. We used to just drop them in the ocean. Now they're kind of cool to watch land. So that's all a catheter is. And catheters can have balloons. And catheters can hold valves. They can position valves. You can use them for measuring pressures. So a catheter is just a tube that you can direct inside the body. Did I get all of that question?
And where does it get inserted when they're putting in?
Oh, where does it get inserted? So for Harmony, it gets inserted in your groin, right in the area between your leg and your thigh, right there. There are two, right? As your body goes down, you have an artery and a vein that goes through your leg, and so they cut down with a needle and they go into the femoral vein. They open it up a little bit and then they slide the catheter in, and you track it through the vein. It's kind of like a blood highway.
Wow, that was a great explanation. Are there any social justice or ethical issues that you notice in your line of work?
So I'll take a swing at this. But if you've got a question, I mean, if you want to say something, just say it, because I just want to make sure I get this. I mean, there's always ethical issues, right? And you're always weighing things off. I mean, one of the obvious ethical issues is animal testing, right? And it's even an ethical issue with a clinical study. Should you use it on the patient? I work in an industry that's risk-based, which means that is the benefit greater than the risk? And those are questions that I take very seriously and Medtronic takes very seriously. We don't test on animals any more than we have to. And as a matter of fact, I've worked really hard to generate silicone models. So when we train physicians, we're not just using an animal to train a physician and discarding it. And they're treated ethically and humanely. So that's kind of one. The other area is healthcare. I mean, there's people that just can't afford to get this procedure. There's people in third world countries. I was in Africa for a month working with rheumatic heart disease. I mean, people are suffering and dying for, things that we have here in the U.S. that other people don't have. Did I kind of hit where you wanted me to hit? If I didn't, be more specific for me.
Yeah, I think so. Yes, that was great. And then we have a question. Does the heart have to have a certain level of health prior to installation of the heart device?
Does the heart need to have a certain level of health? So the heart device, no. Surviving the surgery, yes. So, right, heart failure, in most, right, we talked about how these valves open and close, right? The fluid goes through them, high pressure, low pressure, they open. Well, if you end up in heart failure, right, what happens is the heart stretches and grows and kind of atrophies. I mean, imagine, like your tissue, if for some reason, it gets old. Imagine me, my face is getting older, I got wrinkles, I'm getting a little saggy in my neck, right? It does that. Well, putting Harmony in actually prevents some of that pressure that is causing the heart to stretch. And that something that happens is called remodeling. So when you remove that stretch pressure, the heart actually closes a little bit. And that's a good thing. It's the same with chemical, right? We talked about heart failure if your chemistry's off. Well, your heart can stretch due to chemicals, and then your valves don't close, and then it starts to stretch. You take some drugs, get rid of the extra fluid, your heart shrinks electrically, right? If your valve is not signaling right, you get the beating that can do that. usually the biggest issue is just the recovery and surviving anesthesia, right? So that is very often, so, you know, as the technology advances, they want to do it with less and less anesthesia and time. So, I mean, the Harmony procedure takes 12 minutes, right? Versus open heart surgery, which takes 4 hours. So maybe the answer to the question is device, no, procedure, yes.
Mm-hmm. So just moving to the worksheet, on the question about when students are asked about common diseases on the left supply arterial side, how should they go about answering that question?
Yeah, so the reason that I put the left side of the heart versus the right side of the heart in there is I would answer it is the left side is old people diseases, right? Left side typically wears out because you get old and calcified. On the right side of the heart is more congenital issues, is that you're born with it and trying to solve it. So, you know, even understanding that there is a left and a right side of the heart. And again, I mean, I live and breathe this stuff, Milo. So maybe the nuance here is a little much. But on the left side of the heart, you have the aortic valve and you have the mitral valve. On the right side of the heart, you have the tricuspid and the pulmonary valve. So for me, left side of the heart is more old people and aging and calcification, and it's a big market. Right side of the heart, pretty frequent, you know, affects all of you and your peers. You know, you probably won't have to try too hard to find somebody that's got some type of congenital heart defect.
Well, I have a lot more questions, but I think we need to get to the worksheet. So,
so Milo, maybe just one thing that I wanted to throw out to everyone. The reason your heart is so important and heart failure is such a big deal. I mean, if we think about these power safety shutoffs, right? I mean, I live in Sebastopol, I've got a well. If I lose my electricity, I mean, it gets difficult to eliminate waste, right? It gets difficult to cook dinner because I don't have any water coming in, right? I can't control what's going on because I have no internet. So think of your heart, I mean, and taking care of your heart is like being prepared for a PSPS, right? You want to avoid a PSPS, but if your heart stops working, it affects your brain, your eyes, your lungs, your kidneys, your pancreas, your liver. And that's why heart health is just so important. Because if your heart starts to have trouble, everything else will have trouble. And I just want you to kind of like think of that in a bigger context.